So this question number 2 is asking us to determine non-permissible values of theta. We're going to do that last. I want you, when it says solve, you're going to find everything. So that angle, all the sides. All the angles on all sides, yeah. What we're going to do is we're going to prove the identity first, and then we'll talk about non-permissible values afterwards. So in proving the identity for both of these, if we use the common strategy of changing things to sine and cosine, we can change cotangent to cos theta over sine theta. We can change cosecant to 1 over sine theta. Then I have a fraction over a fraction. I multiply by the reciprocal. And if you're multiplying and factors are identical, you can simplify them. But we can only simplify if we're multiplying and factors are identical. So here they simplify perfect. Then part A, the non-permissible value, I highlight everywhere in my work that I'm dividing. Technically, I should highlight this one too. I look at every place that I'm dividing after I've changed it to sine and cosine. Because technically you're dividing by cosecant as well, but we just have to, once we've changed it to sine and cosine, it is enough to just check at that point. The only thing we're dividing by is sine theta, so does it make sense that sine theta cannot equal 0? Because then you would be dividing by 0, which is not allowed. So then I ask myself, well, when is sine theta equal to 0? We listed our zeros in chapter 6, right? They were k pi, where k was an integer. So now the non-permissible values is that theta can't equal k pi, where k is an integer. Because all of those would cause you to divide by 0. For the second one in part B, we do the proof again. Again, change things to sine and cosine. The only thing you need to change is the secant to 1 over cos theta. But then we get this main idea of what do we do when we have fractions inside of fractions. And if you have fractions inside of the fractions, the strategy that we've been using is you need a single fraction on the top and the bottom of your main fraction. The top, 1 plus cos theta, you can make that a single fraction by just writing 1 plus cos theta over 1. Because it technically does have a common denominator of 1, and you could write it as a single fraction. The bottom, we need a common denominator in order to add, and once I get that common denominator of cos theta, on the bottom I get cos theta plus 1 over cos theta. So our goal is to get a single fraction in our numerator, a single fraction in our denominator, then you can multiply by the reciprocal. If you try to multiply by the reciprocal earlier, before you've got a single fraction on the top and the bottom, the math falls apart and everything goes back. So it's important that we get a single fraction in your numerator, single fraction in your denominator, then we can multiply by the reciprocal. When I multiply by the reciprocal, I put blue brackets because factors, whenever you're adding or subtracting, those factors get grouped together. And so once I group them together, I do notice those factors are identical, so I could simplify them, and I get cos theta, so my proof is done. But then throughout the whole thing, I've highlighted everywhere that I divided. I divide by cos here, I divide by cos there, but then when I multiply by the reciprocal, now I'm dividing also by 1 plus cos theta. So for my non-permissible values, I've got to check, okay, cos theta can't equal 0, because then I'd be dividing by 0 in these places. And the zeros of cos theta were pi over 2 plus k pi, where k was an integer. This is from chapter 6. I also would have that cos theta can't equal -1. That happens when your pi plate at pi. And then if you write everything coterminal with that, this is like a general solution, you get pi plus 2k pi, where k is an integer. So asking the non-permissible values is actually a complicated question because it involves coterminal angles and it involves general solution stuff that we've done before. I wrote down the questions that you can do for practice there.